Now let us look at the second part of elementary matrices and matrix equivalence. Till now we have been focused on row operations. So let's look at column operations. Column operations change the association between variables and their coefficients and hence do not preserve the system of equations. That is, if we are looking at matrices in terms of systems of linear equations. Hence, they are not used in solving systems or in defining row echelon forms. However, column operations are useful when studying the structure of matrices. Each elementary row operation, as we saw in the previous session, can be effected by pre-multiplication by a corresponding elementary matrix. Now, we can say that each elementary column operation can be effected by post multiplication by a corresponding elementary matrix. For example, row operation, we have already seen this. We apply an operation to the matrix A, right? We apply the same operation to the identity to arrive at an elementary matrix. Multiplying E and A, that is pre-multiplying A by E, gives us the matrix 1, 2, 3, 2, 1, 0, 7, 8, 9, which is what we had as the transformed A through this operation. Now, when it comes to column operation, we have the same matrix A, and now we are carrying out the column operation C2 minus 2C1. C2 minus 2C1. So 2 minus 2, 0. 5 minus 8, minus 3. 8 minus 14 is minus 6. We apply the same operation to the identity, that is a column operation, to get 1 minus 2, 0, 0, 1, 0, and 0, 0, 1. So let's say this is F. So this is another elementary matrix. Now if you multiply A and F, that is post multiplying A by F, we get 1, 0, 3, 4 minus 3, 6, 7 minus 6, 9, which is the same as the result of applying this operation on A. Thus, elementary matrices provide a matrix representation of row and column operations. So, two matrices are said to be equivalent if one can be obtained from the other by a finite sequence of elementary row and column operations. We write A equivalent to B for such equivalence. When only row operations are used, we write A equivalence sub R B and refer to it as a row equivalence. And when only column operations are used, we write A equivalence sub C B and refer to it as column equivalence. Now let's look at theorem 4. Two matrices A and B of the same order are equivalent if and only if there exist invertible matrices P and Q such that P is equal to PAQ. Let's prove this. Suppose A is equivalent to B. Then B can be obtained from A by a sequence of elementary row and column operations. Each elementary row operation is equivalent to pre-multiplication by an elementary matrix. This we have seen in the previous session. Each elementary column operation is equivalent to post-multiplication by an elementary matrix. Hence, after a finite sequence of such operations, we obtain B is equal to the sequence of elementary row operations times A times a sequence of elementary column operations. B is equal to the product of a sequence of elementary matrices times A times the product of a sequence of elementary matrices. Let P be equal to E sub 1 times E sub 2 dot 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 E sub k. And let Q be equal to the product of the post multipliers or post multiplier matrices. Since each elementary matrix is invertible, we saw P and Q are invertible matrices. Thus, B is equal to P, A, Q. So, starting from A is equivalent to B, we have arrived at B is equal to PAQ. Now, let's look at the converse. So, conversely, suppose B is equal to PAQ, where P and Q are invertible. An invertible matrix can be reduced to the identity matrix by a finite sequence of elementary row operations, each corresponding to pre-multiplication by an elementary matrix. Reversing these operations, the original matrix can be expressed as a product of elementary matrices. Since P is a product of elementary matrices and every elementary matrix is invertible, it implies that P inverse is a product of elementary matrices. So P inverse is equal to the product of inverses of the elementary matrices. Similarly, an invertible matrix can be reduced to the identity matrix by a finite sequence of elementary column operations, each corresponding to post multiplication by an elementary matrix. Here, Q is a product of elementary matrices. So it follows that Q inverse is also a product of elementary matrices. So Q inverse is equal to the product of inverses of the elementary matrices. If we start with B is equal to PAQ, then by pre-multiplying by P inverse and post-multiplying by Q inverse on both sides, we get P inverse times P times Q inverse is equal to P inverse times P times A times Q inverse. P inverse times P times Q inverse is equal to, now if we group P inverse and P, Q and Q inverse, what happens? Those products will be the identity. So we end up with P inverse times P times Q inverse is equal to I times A times I. And I times A times I is nothing but A. So we have A is equal to P inverse times B times Q inverse. So pre-multiplication by P inverse corresponds to a sequence of elementary row operations, and post-multiplication by Q inverse corresponds to a sequence of elementary column operations. Hence, A can be obtained from B by a sequence of elementary row and column operations, and therefore A is equivalent to B. Importantly, if B is equal to PAQ, then P and Q are not unique. There are many sequences of row and column operations that can take A to B, and these give different pairs of P and Q. Another way to look at this is by incorporating any invertible matrix R of appropriate order. So we can say B is equal to P times R times A times R inverse Q, which gives another pair. That was elementary matrices and matrix equivalence part 2.